going live. For those of you joining us online, we are just checking to see the stream is going okay. But good to see you for the recording. Jeff, how's the stream going? Can we check on YouTube? Started to see what's going on. Yeah, we should be live.
Okay.
Okay, looks good then. Looks good. We might as well get started then. So hello everyone. If this is your first time coming to a CPM Stock event, I'm Brendan. I'm one of the math directors. This workshop will be on inequalities. We'll elaborate a bit on what that's going to be about in a couple of seconds, just to introduce the people that will be presenting these slides today. We have myself, Jeff, and Veer. We worked on the slides together with two others from our team, Peter and Shub. They put a lot of effort into the slides, but they unfortunately couldn't make it today to present. So me, Veer, and Jeff will be doing so. I'm excited to see you all here. We're hoping to have a bit of fun today with inequalities and hope to see you at more events. Does anyone have any questions before we get going with the slides? Okay, sweet. Right, so basically the gist of today is we're going to be looking at a series of different inequalities, some that you may have seen in high school or extensions of inequalities you would have seen in high school. Some of them are more theoretical, but at the same time, we'll still be trying to, especially towards the end, to give more useful techniques to solve inequalities on some more case-by-case basis. But hopefully by the examples we'll give, you'll see different insights as to different tricks you can pick up in solving inequalities. But first, we should talk about why we care about inequalities at all. So if you've done, say, extension to maths or some type of equivalent at another institution in high school or early first year, you would see questions and scenarios which come down to, I give you an inequality and ask you, hey, prove this inequality is true. So in that case, yeah, you're given an inequality, you need to prove it's true. So of course, naturally, you want to develop techniques to prove inequalities are true. And so that's the side that would show up in competitive mathematics, where in an Olympiad or something similar, they give you an inequality, ask you to prove it, and you spend 3 hours and maybe not get much of anywhere. But hopefully, with some of the techniques in this workshop, you could get somewhere. But for me, I don't actually have the biggest experience in competitive mathematics to compare to some people in my team. I study pure math, and personally, I found when I did some pure math courses in second and third year, actually there are quite a lot of uses and quite a lot of nice relationships between inequalities and some very important notions within pure math. So what an inequality gives you, if you think about it, is it's a comparison between two quantities. And what that means is you have this notion of being able to give an upper bound or a lower bound in quantities. You're able to get a scope of how big a certain quantity can be or how small it can be. So bounded above, bounded below. And there are certain applications to that. The ones that I'm familiar with are in extreme graph theory, where you can look at different types of bounds and different number of graphs that can exist, and other parts of combinatorics where you're trying to count how many objects exist of a certain property. So pure math circumstances like that, where you're trying to count and enumerate and so forth, how many different types of objects can exist, you give upper bounds, lower bounds for that. But also it's very fundamental to an area of pure math called real analysis, because it's fundamental to a notion of convergence and limits. We'll explore in a second some nice inequalities, triangle inequality, Hölder's inequality, and so forth, that come from, that have uses in proving convergence and limits. Convergence and limits come down to a notion of being able to say how close certain quantities get. So that's useful, and it has many applications when you're solving, say, differential equations and making approximations like that. Admittedly, I don't know too much about it, but notions of convergence and limits gives you certain assurances as to how quantities grow and approach a certain value or certain functions that you want. And the way that you prove that type of convergence and limits is through inequalities. They give you the upper bounds that you want to say something eventually gets small enough, some quantity you could say that is referencing the sense in which you converge, if that makes any sense. Any questions? Otherwise, we'll get actually into the inequalities now. Cool. And I guess one thing I should mention, just to explain maybe the analogy I was using in the marketing, we call this workshop the constructing inequalities workshop. In a sense, you have this vision of the inequality you want to prove, and you have certain techniques that you can prove it with. There's kind of an art, and similar to construction, in working out which techniques you want to use together to prove your inequality. Just to explain that. So that should be enough flavor for and motivation for what we're about to get into. So I'll hand it over to Jeff now. First, please send the attendance form while I switch over to Jeff. We'll get into the first section. Please scan the attendance form. Jeff, come up and we'll get cracking.
Huh? Oh, there's no vent.
Right. Just take this. Wait, don't turn it.
Oh, yes. He doesn't not reach out one final right there.
Of course. I'll put it in. Yeah. Actually,
Live streaming.
that's true. That's true. Yeah, Esther, how about you do it then?
Yeah.
Yeah. Sorry, people, we're just having some technical difficulties. So, if you want to use the weapon, I'll use
Well, I never understand words. No, I'm not.
yeah, do you want to use the mouse? Can you scroll
No.
Square.
Right.
There.
Is it there now?
Yeah, no.
Can someone confirm?
Wait, let me scan my QR. There's a number.
That's what I'm asking you.
Oh,
Okay.
Hey, thanks, Esther.
Yeah, so I guess you can fill it out in the meantime. Please scan the QR code for me. Yeah, so you guys can fill it out in the meantime. Anyways, I think the first inequality is the most important one, like ever. The trivial one. If x is a real number, then its square is always going to be greater than. This is the most important one. Right? So if I square a real number, it's always going to be greater than or equal to 0.
Why?
What do you mean why? Because you don't have square roots of negatives. That's why. Yeah. I haven't worked in, but yeah, I guess if you know about some squares, you can use that as well. I'm going to use this later on in the proof of like AMGM, so that's how you know it's important. But yeah, just keep this in the back of your mind. Okay, but here's our first like real inequality, triangle inequality, and what it basically says. Well, okay, of course, it's one of the first ones that most people see, but what it says is that if I have some real or complex number like say and G, then you can kind of like separate the absolute value if you found it by above. And then I also included the circle inequality, which is also called, I believe, reverse triangle inequality. It's in this form. But generally, when you say triangle inequality, we're talking about this here. And then what that included, like, hold on. But why is it like called that, right? Like, where's the triangle? I didn't see a triangle. Well, it's like, imagine you have a triangle like this. Let's just say, let's just say this is Justin's home. So I write Justin's home, and then this is uni, right? Justin, he can go straight from his home to his uni, but he also really likes Guzmán Gomez. So he could go to GYG on the way to uni. But if he goes to GYG first, he's going to take longer, right? And that's basically what the triangle inequality is. It's, well, if I take this path, it's longer than just going straight to that
So
path.
is that why Justin's always late?
That's why Kevin's always late. Yeah. So yeah, it's basically saying that like if you imagine these side lengths like a plus b as like a side length c, then the sum of the other two ones is going to be greater than that side length. And then of course you can extend this to n terms as well, so you can kind of expand out the absolute value in a sense. Hello. But what I was kind of just saying there was pretty much like the vector version, which is I can replace the a and b now with like real or complex vectors in n dimensions. And in this case, well, if I label it like this, maybe not this. This would be like a plus b, and then this would be like, sorry, this would be a plus b, and then this would be like a, and then b. And then, as you can see, the length is going to be longer in that case. And then, if you're familiar with linear algebra, then you might be familiar with this. It doesn't apply to just any like complex vectors. It can apply to any vectors in general if you have a normed vector space. But don't worry if you haven't seen this. Don't worry about this. If you haven't seen it, I feel like a math nerd, you know all about this, but yes.
So we look for any?
Yeah, it's like literally in the definition of a norm.
That's cool.
You need that. Yeah, so if you haven't seen it, don't worry about it. I just included it for funsies. You might also see it as being called Minkowski's inequality if you've done measure theory. But don't worry about it if you haven't seen it. We're mainly going to focus on this one and the previous one here.
Sorry, Tito.
Yep.
So left side's A on the triangle.
Yeah.
You need to GYG A. GYG is the
Oh, sorry, GY needs to like Justin's house and then there. So it'd be like A plus B, which is going to be that.
Yeah, if he goes to GYG on this way, you can go this further this.
Yeah, so this would be like A plus B.
And that's why it's always late.
Okay, so oh, let's see. All these markers. The new mark is literally A. See,
So how can A plus B be less than A plus B? Am I missing the truth?
well, it's like imagine the lengths of these right lengths. Like you're traveling like some length here, and then you're traveling some length like here. But like you're kind of like going outwards from the path. You're kind of taking a detour, right? As opposed to just directly going like that way.
Oh yeah.
Yeah, because
It would be
Yeah.
but
in this case, like taking the detour would be represented by this like here. So you first travel the length of like A first, and then you travel the length of B. As opposed to just traveling the length of A plus B, which is this vector here. Yeah. Okay. Yeah, it's also called triangle inequality because we can use it to like bound our like side lengths of triangles. So if you say know like two side lengths of a triangle, you can know the length of another side, or like bound for it at least. Which is exactly what we're gonna do in this question here. So if we have oh my god, I was stepping on the mic. Oh. Sorry to the people on the line if you heard me kicking the mic. Anyways, yeah, so let's just say n is a positive integer, and then we have this triangle with these weird side lengths, log base 10, 12, log base 10, 7, 5, and then log base 10, n. And then what we're tasked to find is how many possible triangles can there be in this case, right? Yep. Oh, yeah. I'm just gonna move. And then what we can do is we can just let A, B, and C denote the like sides of the triangle. So kind of like what we've done here, right? And let these be like the vectors denoting the sides. And then we'll label them with these side lengths respectively. So when we use the triangle inequality, because we know that, well, like this side length is going to be smaller than like these two added up, right? You get this log base 10 and it's less than that. And when you rearrange for n, it's less than 900 in this case. And you could take a different pair of like sides, and then you can eventually find that there's another bound for n, which is n has to be greater than 6.25. And we should also check if, log base 10 of n is going to be greater than 0, because obviously you can't have a negative side length. But since n is already going to be greater than 1, it doesn't really matter, because once you go below n equals 1, you're going to have like log base of like something less than 1, which is going to be less than 0. So that's already fine. So basically we have that n is between 6.25 and 900. And then if you just like calculate how many numbers there are in between, or like integers in between, there's 893, which is the answer. So there's 893 possible constructions of the triangle with these possible side lengths in this case.
Wait, one question.
What?
So the sides, your supposed sides satisfy that triangle equality.
Yeah.
You know you can construct the triangle.
Because you can. If you have a good enough ruler, you can construct anything.
Yeah, but how do you know?
Sorry, it's what you get 6.25. You don't have to apply it in the works or the 6.25.
Yeah, maybe explain that.
Oh, you can pick like you can do like log base 10 of n plus log base 10 of 12 is less than log base 10 of 75. Or you can do the other way, like log base 10 of n plus log base 10 of 75 is less than. Sorry, it's greater than 12.
That makes sense.
Yeah, you can just pick. Yeah, there's two different pairs you can pick pretty much. So apply it to. So I guess the next major inequality that we're going to go through is Cauchy-Schwarz. And what it basically says is if I have these numbers a1 to an and then b1 to an, the sum of them like multiplied squared is less than or equal to just the sum of them squared like multiplied. Kind of hard to state in words, but you can see it right there, basically. And again, if you're familiar with linear algebra, you would have seen this. Of course, if we just make the inner product to be the standard dot product, then we get this result here for R. But of course, don't worry if you haven't seen that. We're going to be mainly using this one here in general. There's also another form of Cauchy-Schwarz which is like very useful. So it's the angle form, or you might also have seen it as like I think like Type-2's lemma or something. And this is a very like useful one, as we'll see with the question. So it's a nice form of it, and there's a quick proof from Cauchy-Schwarz. We basically consider this sum squared, and then we multiply and divide by bi, which we can do because bi is always greater than 0 because b is a positive number. And then we just apply Cauchy-Schwarz to like these two terms here, and then we get this from our normal Cauchy-Schwarz. And if you just divide by sum of bi, then you get the result. Yeah, so it's a nice quick proof. So let's see that in action. So we have this very, very elegant looking like inequality here that we have to prove. But thankfully, we know Cauchy-Schwarz, so we can just choose it in like 2 lines. So let's just say our xi is ai, and then our yi is ai plus bi. Well, we know from the angle form that this inequality is true. So just plugging in for our xi's and yi's, you get that this sum here, which is the left-hand side of this inequality, is greater than or equal to the sum of all the ai's over the sum of ai plus bi. Well, we know that the sum of the ai's is equal to the sum of bi's, so we can just rewrite this as twice the sum of all the ai's, and then that obviously simplifies to just sum of ai's over 2. And then we get the right-hand side there. Any questions about that? Yeah. AMGM, so this is like the main one, I guess, like everyone uses. Yeah, so hopefully you've seen this in HSC, but if you haven't, it's basically the arithmetic mean is always greater than or equal to the geometric mean. And if you don't know what that is, again, then it's basically the same here. So if I take like the average of like these n numbers, or it has to be positive real numbers, then it's greater than or equal to like the nth root of all the products, basically. And then yeah, obviously there's equality if and only if all the numbers are equal. So here's a little like visualization of like what's going on. Well, we're gonna work on it for like a 2-dimensional case, so not 2-dimensional, like 2 number case. So we can consider this like circle with what diameter AC, and then we're gonna pick some point B, And we're going to say that AB has length A, and then BC has length B. And then we can find the length of OB by subtracting the radius, which is obviously A plus B over 2, and then obviously the length of AB, which is A. So we get that length of OB is B minus A over 2. And then if we use Pythagoras on the triangle OBD, then we get that the height, which is the length of DB, is AB. Oh, sorry, the height squared is AB. But now we know that, well, the radius, which is A plus B over 2, is the hypotenuse of that triangle. So it must be the longest side of that triangle by like Pythagoras, basically. So we get the inequality here, basically. So the hypotenuse's length is greater than or equal to this side's length. That's like the geometric intuition behind, like, I guess the 2 number case. But let's actually look at like how to prove the n number case. So the easiest way to do this is by using Cauchy induction. And in case you don't know what that is, you just prove the base case for 2 variables. And then you prove this, the forward step. So if it holds for n variables, it holds for 2n variables. That's the like induction part number 1. And then if it holds for n variables, you have to check if it holds for n minus 1 variables. And that's Cauchy induction. Slightly different to the normal mathematical induction you might have seen. You can have a think about why this works in the meantime. So, coming back to what I was saying at the beginning, this is the nice, easy proof for the 2 variable AMGM. So, consider this expression squared, which is going to be greater than or equal to 0. And then that means this is greater than or equal to 0 when you expand it. And then rearranging, you get this. See, trivial. Now for the forward step. So you consider A and B, and you let them be like these forms. And then since we're assuming that the n variable AMGM is true, we know that A is going to be greater than or equal to that, and then B is going to be greater than or equal to that. And then we can just use like the 2 variable like AMGM here to get that result there, which is proving it's true for the 2n case. And then for the backward step, so we let A and be that, and then A is going to be that. And then we use the n variable one on that, which is equal to that when you solve it. I know I'm saying that a lot, but like try saying all of that like in one breath. Yeah, and then you use the n variable AMGM here, which is going to be greater than or equal to that, and then you simplify it here, and you get the result for n minus 1. It's, yeah, it's kind of hard to say like all of the things, especially at once, but I hope you get the idea at least of like roughly how the proof works. So here's like a nice example of like how to use like AMGM. So we want to prove this inequality here, which looks very ugly again, right? But because we know AMGM, we can kind of like solve this in a very quick time. So we can consider these like expressions here. So A cubed over BC plus B plus C. And then like a similar expression here for B and C. And then using the 3 variable AMGM on each of these, you would get that this is greater than or equal to 3A, that's greater than or equal to 3B, and that's greater than or equal to 3C. So like you just multiply all these together and then cube root and then multiply by 3 basically. And then we just add all these inequalities. Why is it not going to the next slide? Okay. We just add all 3 together. So then you get the left-hand side plus 2 times A plus B plus C is greater than or equal to 3 times A plus B plus C. And then you just rearrange and you get the result that was in the question. Yep. So that's like the end of my part. So I'll just give it to Via now. We're going to talk about Jensen's. So Jensen's is also another like very powerful inequality. They're all very powerful, except maybe stuff. Yeah.
Sorry.
Turn it off.
I forgot where the switch was from. But Jensen's is actually very powerful.
Why are there so many people on?
How many you can
One.
Yeah.
I hope everyone's hyped for Jensen's. This is actually, as Jeff said, a pretty powerful inequality. Like, sometimes people tend to gloss over it, but it has a lot of applications. But before I start, I'd like to say this is also used in statistics and finance as well. So it not only limited to competitive mathematics. However, the competitive applications more funny, I would say. But yeah, before we start, we need to talk about two concepts, convexity and concavity. They are very important concepts. You might have seen this a little bit in high school, depending on which topic you have covered. But at least convexity, the whole idea of it comes, like say you have a convex function f, somewhere in the curve, it's going to look like this. Let's just say you have two, okay, sorry, my bad. Let's just say you have 2 points, x1, x2. For a convex function, when you draw basically a secant, this chord here in the interval x1 and x2, just saying, obviously x2 is greater than or equal to x1. Just to note that. This chord here, any point on this chord lies vertically above any point on this curve, or at that point. So, let's just call this point C. So this point evaluated on the curve FC is actually less than or equal to the point on the secant. So that would be, if I describe this as, let's just say a T1 minus T ratio split across the interval, that would be less than T T1 minus T, we've defined this as T1, T2 in the slide, so that would be Tfx1 plus 1 minus Tfx2. This is the fundamental definition of convexity. So the whole idea is you have the coordinate secant lying above the function, which is why a point on the function and on the secant for the same x has the point on the function less, f evaluated at that point less than the y value on the secant. So this is very fundamental. This will determine Jensen's inequality for almost the rest of the slides. One thing to note is that convex functions also have the neat property that the second derivative of the function is always non-negative. So by being positive, they demonstrate that convexity argument, and by being essentially equal to 0, they have the equality that will show up in Jensen. So this is a very important property of convex function that we'll use later twice. And similarly, there is concavity, which is pretty much the opposite of convexity. So in this case, I'll probably just use the same diagram, but redrawn. So in this case, a convex function would have some sort of curve looking like this. And you would have the function evaluated at the point, that value vertically exceed the point on the chord or the secant. And this is also very important because concavity is used for reverse Jensen's inequality, which I guess is Jensen's with the inequality sign flip, basically. Similarly, the property of a concave function is opposite. Roughly, you still have the equality, but f dash dash x is less than or equal to 0 for a concave function. I hope that made sense for the prelude. Any questions before we get to the tastier parts? So I hope that part makes sense about convexity. Just to note, before we get there, as you guys can see, this form I described with t, 1 minus t, essentially, these two coefficients that are attached must sum to 1. That's very important. And we'll be using it a lot in our proof for Jensen's. I'll just clean this for a moment. Yeah, Jensen's, I think, is one of my favorite inequalities, just because the application is almost limitless. And here's one thing you might have learned in high school that might inform Jensen's. You might have learned this notion that for certain functions, essentially the midpoint or so-called mean value is potentially greater than or equal to the actual point if that function is increasing. So this is one of the applications of Jensen's that's been done in high school, but we'll expand more on it. So now the meaty part will come. As I said, Jensen is informed by the convexity argument, which is why we have to introduce convexity. It's very powerful. You can use it to derive weighted AMGM and all sorts of inequalities. But yeah, this is basically Jensen's inequality. I guess more generally, f of the weighted sum for a convex function is less than or equal to the sum of weighted sum of f's, like the values, for a convex function. And for a concave function, it's just you flip this around. That's Jensen's inequality in its fundamentals. I know at this point it might look a little weird seeing so many TIs since we were used to just T1 and T2 and that sort of logic, but this does hold true. And we can actually prove this by induction, Jensen's inequality. There are other proofs to Jensen's as well, but induction might be the most intuitive proof at this moment. So the base case. Any ideas what we're gonna do for the base case? You guys might actually laugh. Okay, we'll use the power of the convexity argument. So basically we do the same setup. We on an interval of I guess x1, x2, we define essentially two ways, t1 plus t2 equals summing to 1. And we're going to use that for our ti fxi logic. So we're going to use that. And as I said, you can express any point on the secant there as, on the interval there as t1 x1 plus 1 minus t1 x2. This is sort of like, if you guys remember vectors, parametric notation, that's sort of where it just comes from, except we're not dealing with two-dimensional vectors necessarily. And after that, we're literally going to use the convexity argument. So our base case technically doesn't need any rigorous proving or algebra, because we're literally invoking the power of the convexity argument, because Jensen's for the base case is literally this. So you do the summation from to, so which is why you have the argument that f of t1 x1 plus t2 x2 is less than or equal to t1 f of x1 plus t2 f of x2 for a convex function. I hope that was clear. It literally just invoking the convexity argument, and you'll realize that this thing you see for n equals 2 Jensens is literally the definition of convexity, which is why we can call upon that to make the base case true. I hope. Any questions? Alright, so now we'll get to the meteor part, but before we get there, this is a neat little diagram. I think Schumann made it, yes, it's a very good diagram. He used ticks, I believe. But as you guys can see here, that's the point on the chord or secant in that interval lying above the function value for t1 x1 plus t2 x2. It's here. And now we get to the meteor part. I think you're gonna like this, Jeff. So, for to start with, we're going to use basic induction, which is why we're assuming Jensen's holds true for n equals k, where k is a positive integer greater than or equal to our base case. And we're basically meant to now have the induction hypothesis, which is assuming it's true for n equals k, can be proved it's also true for n equals k plus 1, if everyone recalls that from a prior time. This is still very powerful, even though it's more of a high school era technique. So now we get to the meatier part. I know this proof seems a little lazy just starting off with a line, but the intuition comes later on. So the first thing here is we have our left-hand side of the inductive hypothesis that we need to prove. That thingy, we split it up into a sum from I equals 1 to k, because we have a sum from I equals 1 to k that follows Jensen's inequality, and this is the residual. Now, does anyone have any neat little ideas what we'll do next? I'll take a note of the fact that we literally took this guy out of the summation. Any ideas on what we're going to do next?
You use the inductive hypothesis.
Close. We're going to do it after. So you are correct. But what are we going to do in the immediate vicinity of next? That is after this.
Use Jensen's.
Yes. We're going to invoke Jensen's for n equals 2. Because by base case, we know that works. So when we invoke Jensen's, we're able to split this into a tk plus 1 weighted sum of, fxk plus 1 and a 1 minus tk plus 1 weights to this guy. And now we're going to reach to your point. But before we do that, anyone have any ideas why we're able to call Jensen's? Like, you guys know that this is less than 1 and this is less than 1. But do you know if they sum to 1? You guys know that? That's good.
Yeah, because if you plus them, don't.
Yep. Yeah. I was just doing a neat little sanity check because sometimes you can get a little lost in algebra and logic. It's good you guys know that. But now when we're meant to apply Jensen to the next part, do you guys know why this guy sums to 1? Any takers for the algebraic working out? I gave a little tease there.
You just sum it up. It's 1.
But more rigorously, you guys all know that T1 plus all the way till TK plus TK plus 1 equals 1, like we started off in our induction statement. So T1 plus all the way till TK equals to 1 minus TK plus 1. Which is why, when we divide by 1 minus TK plus 1, we know that all our TI, 1 minus TK plus 1, will sum to 1. And that's why we're gonna next use our inductive hypothesis and actually apply Jensen's. So now comes the powerful part. When we actually apply Jensen's, we still have this term here, but we've converted that function evaluation of sum to sum of fxi weighted. After that, just a neat little bit of algebraic manipulation, and we reach our right-hand side, which means we have proved that it is true for n equals k plus 1, given it is true for n equals k, and our inductive hypothesis has been proven true, so we're then able to conclude it. Did that make sense? Nice. We're gonna get to some more fun applications very soon. And this is a simple application. Has anyone seen this before? Just curious? I know Brendan and Jeff would have, so I guess both of you are exempted from the survey. I know it might feel weird at first glance. Where do I apply Jensen? But the intuition is, notice that A to the B, C to the D, there's a bit of exponentiation. And what's more closely related to exponentiation than logging? So our ansatz is that we're going to apply Jensen with the log function. And Jensen's with the log function is actually a very common application. It's used in probability, and it's also used for proving weighted A and GM. So that's our current answer so far. But before we actually reach to applying Jensen's, we need to consider how we can actually tackle this such that we can apply Jensen's. So firstly, note with the question that B plus C plus D plus E equals 1. As further affirms, we should apply Jensen's because we have a necessary condition we need for Jensen's. Now, I guess the main idea would be to know why log. Anyone have any ideas why we're going to do log for Jensen? Yes.
Because we have something on here, like the small piece of music.
Parts. Small. Yes. Yeah, the powers. That's why we got our ansatz. But the main thing to note is that the second derivative of the natural log, so that's the d squared on dx of ln of x, is the d on dx of 1 on x, and that's negative 1 on x squared. So we have ourselves a concave function that, as we know, is also increasing. That is one of the reasons why we can't use log, because we have a function that's valid for reverse Jensen's inequality. Now, anyone ready to do some algebra bashing? Alright, so we have our ansatz that we're using log. So let's just consider the natural log of the left-hand side. LHS stands for left-hand side in this case. I've noticed some courses at UNSW, they want you to define LHS first. So if you ever do this in the uni exam, do keep that in mind. You may need to define what LHS is. So the natural log of AB plus BC plus CD plus DE. Yes, the natural log of that. And so that's where we should start off. I just realized I had to actually get here first. So now we know that we have our B, C, D, and E actually meeting the conditions for Jensen's. So does everyone think it's plausible we can apply Jensen's right here? We know our function is concave and we have the right weights. All good to Jensen? That's good, because that's exactly what we're going to do. This is greater than or equal to ln A ln B plus B ln C plus C ln D plus D ln E. After that should be a neat little application of log laws. You guys should know that the coefficient next to a logarithm can be taken inside right here, which is why this expression simplifies to ln b to the a, all of that, ln e to the d. And after that, I hope everyone recalls the next law. It's literally sum of logs is the log of the product. So ln b to the a. No wait, yes, ln b. Ln. No wait, sorry. Did anyone see the mistake I made?
Sorry, what was it?
That's okay. We're all here to learn. A is not meant to be the weight. The weight is B, C, D, E. Keep that in mind for when you actually are solving the question, that your brain needs to stay awake. Otherwise, there might be consequences.
Yeah,
Are you sleepy at 2 p.m.?
yeah.
We all are sleepy, I think.
I would have woken up at this time.
So once you recognize what your true weights are, then you apply Jensen's properly. So you have B ln A plus C ln B plus D ln C plus E ln D. That's logical? After that, the same idea, you apply the log law with power, so ln A to the B, all the way summed, ln D to the E. Then the whole sum of logs is the log of the product. So you have ln A to the B to the C to the, ln A to the B, C to the D, D to the E. So right now, we have this for what we're trying to prove. Ln of AB plus BC plus CD plus DE is greater than or equal to ln A to the B, C to the D, D to the E. So that part's clear, right? We're so close to actually proving everything. Like literally. This is how far we reached. Yes.
Shouldn't there be a B to the C term as well?
B to the C. Yes, thank you very much. I need to say wait as well as you guys do. So I shall try my best.
There's a typo in the question as well.
I thought that was fixed.
Like, no, you didn't. Because it's 3 steps. Go back.
Yeah, that's
Go back. There's 3 terms on the right hand side, so 4.
yeah, it would be A to the B, B to the C.
Oh, sorry about that. I thought I had fixed that. Sorry. Yes. I apologize for that. Now we've done this. Anyone know what should we do next to actually reach our final inequality? Any ideas? Yep.
Inverse law.
Yes. But how can we just take that and assume this inequality remains? Well, I just noticed from the fact that exponentials are increasing, so the inverse of a natural log, in this case, the e to the x function, when you differentiate it, is e to the x, which is non-negative, and it's positive, yes. Which is why, as you said, simply exponentiate and you reach the final destination. So I hope that was clear. Any questions? Alright, now we get to the meatier part. This is what we've been building up to using Jensen's. This question that's about to come can be solved using other more potent methods, but I'll show you how to, I guess, algebra bash it out with Jensen's. So, behold, this is the question. And this looks a little scary, right? Or is it funny? Or both? Yes, so this is the question. Any thoughts? They haven't even given us the conditions for Jensen. Can we really even use Jensen's for this? Yes?
It's like quadratic solution, right?
Pardon?
Like it's the reverse of quadratic solution.
Ah, you mean the square root? Or
Yeah, like the one of the things.
yes, that's a good spot. The fact that these terms sort of look like they belong to a function, that's actually what we're going to invoke next. So before we begin, let me note that lots of other solutions use stuff like homogeneity, which we'll discuss later. So this solution will not be covering homogeneity, but that's a more powerful technique that will be covered later. So now we go to the meatier part. So firstly, realize that there are no weights. How can we create weights? Because one thing about maths is if the inequality or equation doesn't suit what you're trying to do, sometimes you can alter it such that it suits your purpose. So we're literally going to take 3 out and we will have price the weighted sum of these terms. Now we're one step closer to using Jensen's, but not yet. We haven't identified our function. Anyone have any guesses on what the function could be? Except Jeff and Brendan. Yeah, the next part is a little underintuitive because you just need to be lucky to realize it on the day. But yeah, literally, you have that and you just replace the a with root a squared. So your ansat is when you combine the radical, it should lead you to a more intuitive version that you can use. So when you do that, and then you multiply by root a, you will have root a cubed over a cubed plus 8abc. Does anyone see why this was done? Like, we could have stuck out with that function. The main reason is we're just trying to make sure we have a way of defining the function where we can get rid of having to account for the B and C stuff in the definition, because that changes everywhere. Which is why, by multiplying, we're able to create a much more consistent definition. And similarly, we can do that with B and C, which is why this is our little function. This function, we're gonna use it a lot. Now, next part, I'm gonna spare the torment of computing that's going to come. But note that we don't know if this function is concave or convex. There are many other ways of figuring that out, but given current information, we will have to do some calculus. So it's very easy to differentiate it first using the chain rule. And second, you have to use the product rule to double differentiate it once you get it in a nicer form. And that'll tell you some very important facts. But before we actually use any of the facts, if you go back, just remember what we're trying to prove here. Remember that. So we need to show somehow that the weighted sum, if we are using Jensen's, is greater than equal to the function evaluated at that point. So that means we need to show that the chord lies above the function, that it's convex, which is why here's going to be the little assumption we'll need to make to actually solve the problem. We're going to have to assume that x is less than or equal to abc to the 1/3. Because that'll make this term negative. A negative times negative around the rest of the positive terms, you'll get a negative second derivative. So we'll need to set that constraint up. Now other techniques like homogeneity will be able to get that assumed at the start, but currently we'll need to assume that at this point. And now we can actually apply Jensen's. So next should be really chill. You just simply apply Jensen's. Yeah, that's literally the next part. Now, anyone has any ideas on what we should do next? AMGM. Thank you, Jeff. AMGM. You need to know this result. Very important. Once you actually put that in, your job will get even easier. So you'll be able to literally evaluate this, and then it will get much more simpler. Now you need to know one thing. Why are we able to just substitute this in and not have the inequality change? Any thoughts from just what's there? It's because the function is an increasing function. We showed that with the first derivative. If we go back, as you can see intuitively, there's just mainly positive stuff here. So that is why. And consequently, we're able to use Jensen's. And yeah, that's a thought for later on. How can we remove this assumption to complete the question? Because ultimately this assumption is a restriction for us. And now I'm going to hand it over to Brendan. I hope you are hyped for hodlers, Brendan.
We're hyped. We're hyped.
Let's go. Sorry if I was a little slow, but
So chill. So we're getting towards the last part of the workshop now. So I'll be taking these last two sections. This one will be a bit more theoretical, so feel free to not understand what's going on. If you're new here, it's the basic gist. But for this first section, we'll be looking at Hölder's inequality, which is a very important inequality to real analysis. What it basically is presented here. It's a generalization of the Cauchy-Schwarz inequality. So we saw some slides before that the Cauchy-Schwarz inequality, I wrote briefly, it said that sum, we have the same type of dot product, they will run like this, AI, BI, was less than or equal to the sum of the AI squared, and this is the square root, times sum of BI squared, also the square root. Well, really what you saw on one of the previous slides was that it was looking something like this, and then you could rewrite it with the square root that it before. So I'm just going to rewrite it like this. And just the visual observation between this inequality, your Cauchy-Schwarz inequality, and this Hölder inequality is it's basically the same, but on the right hand side, you're replacing this 2 that's on the denominator of the power and also places the power of the AIs. That's replaced with a P, and likewise a Q is replacing for the B. Specifically, we have a requirement that P and Q satisfy for Hölder's inequality, what we call Hölder conjugates, that is the sum of their reciprocals. Then I guess harmonic mean is 1. Do you want to go that direction? I believe I use that right. And we also need to make sure that P and Q are at least 1. You may be angry at me as to why I wrote the square bracket for the infinity. So maybe an exercise for the reader if you want to work out what happens when you plug in infinity for, say, P or Q. A little hint is that if you let P equal to infinity, then Q is equal to 1. You get a little inequality that you may actually recognize already from that. So try that out. Think about like what the limit of the sum of AI to the power P for 1 over P becomes when you plug in P equals infinity. A little exercise for the reader. And because this section, again, I said, feel free not to understand this, but more generally, what this becomes is the reason why this is important is because what this does, it gives a comparison between inner products and norms. So with the Cauchy-Schwarz inequality, what you see on the right-hand side is the norm of A compared to the norm of norm of B. Let's them together. And I should say the factors so A1 through AN. And you're comparing the size of the product of their norms to the size of their dot product figure. And what Hölder's inequality basically says is you can extend that to get an upper bound for how large your inner product would be in terms of the norms of the two functions, in this case, generalized vectors. So it can be way more general. But skipping over that, we'll get to an example in just a second. The observation here is that what happens when I set P and Q, oh, sorry, didn't go back. What happens when I set P and Q equal to 2 in Hölder's inequality? Yes, thank you. Cauchy-Schwarz comes out of this when you set P and Q equal to 2. Those are Hölder conjugates because half plus a half is equal to 1, shocker. And because that means that we get our favorite Euclidean norm. In other words, the sum of the squares, square root. Okay, so we have this little example here that somewhat resembles what a norm looks like. Let's try this one. So maybe I'll just give you a few seconds to have a look at it and come up with a few ideas while I write off the whiteboard. There's a few things I want to motivate. So you may not know what to do yet, so let's try to choose Hölder's inequality. We know from the previous slide, let's look at which direction the inequality is facing. It's facing to the right, so we have the norm side part on the right. In this case, we're trying to trick you a little bit, we have it on the left. So that means what we want is we want the little dot product type thing to be on the left. So we have this 2 to the power of k plus 1. For a moment, let's just consider that as a 2 perhaps. Oh, this one is 1. Let's unreal. So these were all new markers, so that's interesting.
You got scammed.
What? These were new markers. Sucks. These
Wait, that one sucks?
These are all new. What? Okay.
I think it's that one.
I hope everyone liked that. Okay. Sure. So let's just write it like this, just to rearrange to see where we're going. Okay. So it might not be clear yet what we're going to try and do, but at least to me, this 2 seems like we could maybe get some. What I notice when I look at these is maybe there's some sort of way I could get 2 to try and multiply x and y together. It's not immediately obvious to me how I would do that. But what I can say is what I would start off with is something of the form, maybe we could do something similar to say 2 is of course equal to x times its reciprocal plus y times its reciprocal. X and y are both positive, so we don't have to worry about division by 0. This is maybe a good starting point, and so this kind of resembles a dot product. We have 2 vectors in a certain way, x and y, and x inverse, y inverse. We have to think about then what type of powers that we want. So I could say this is the same as saying x to the a and x to the negative a for any a, and same for y. Could do it like this. We have to think about what type of power we want. We want to use a power that gives us what we would like in Hölder's inequality. And so we have to look again back to, this is green one. We have to look what does these look. Look at our left-hand side. It's not, currently it's a sum. We don't really want a sum. We want more of a product. So let's try to rewrite it. And that's going to move the slides. They've done the work for us. Look at that. I don't have to do anything. Wonderful. So x plus y to the k, so that might be one of our norms. And so it's better. And x to the negative k plus y to the negative k. And since we moved this 1 over k to the left-hand side, well, that's cool. Since we moved this 1 over k to the left-hand side, we'll write this as k over k plus 1, and this one will have a k. Okay, so maybe if you stare at this a little bit, does anyone have any suggestions of what we could use for our p and q values if we want to use Hölder's inequality? Any suggestions? What's maybe something silly? What's something close to what this resembles?
K and K over K plus 1.
Yeah, okay. K and K over K plus 1. I think that's exactly what we want. Yeah.
1 over K and K plus 1 over K. Yes.
But yeah, something roughly like that, yeah. Yeah, close enough. Close enough. Yeah. So that's one way to do it. I'll just write it out a slightly different way on the board. So you can observe that if I write x to the k over k plus 1 here, and x to the negative k over k plus 1, and this is y to the k over k plus 1. I'm going to do it slightly different to the way we have written on the slides. This is a valid equation. We're just saying this is 1, this is 1 because the powers cancel. And if we have p as k over k plus 1 over k, what's going to happen is that when we raise, let's say this is, I'm going to write it as A1 times B1 plus A2 times B2, just to kind of bring in the vector similarity. A1, A2 as a kind of vector would be x squared k over k plus 1, y k plus 1. Likewise for B, B1, B2, we have the same thing but negative. And so what I'm going to do is I'm going to say then Hölder's inequality that tells us that 2 is less than or equal to the AI to the P plus A2 to the P over 1 over P times B1 to the Q plus B2 to the Q over 1 over P. And maybe if I rewrite these two in a slightly different way, this will become a bit easier. P is k plus 1 over q, so we can rewrite these as p. Yes, that's kind of motivating the cancellation that we want. Sorry, 1 over p. So x of 1 over p, 1 over p. And likewise here, it's be 1 over p, 1 over p. Okay. So it becomes a little bit algebraic. We have 2 less than or equal to the 1 over p that we cancel, x plus y that we wanted, 1 over p. That resembles what we wanted. This is 1 over p. And you can do the algebra from here, that this ends up turning out what we want. Let's just see, it's x to the negative q over p plus y to the negative q over p. And that turns out to be k as we want, and this is 1 over q, which is, again, what we want. So you can verify those last few steps in the way we've written down on the board. You can also observe what we did from the slides. Any questions on this? Cool. Okay, so hopefully you appreciate a little bit of the type of link between norms and Hölder's inequality. Okay, so these next few slides will be the motivation towards a certain technique called normalization. First, we introduce this idea of homogenization. The basic principle we're trying to motivate towards is we like equations, similar to how engineers like equations that have basically the same units on every single term. So we saw a few examples of that. I think Bea was talking about, if we go back a few slides, which one was it? It was this one. If you consider every single term, say the term that has A in it, or this first term, the second term, the third term, they all have the same units. If you assume A, B, and C have the same units, say A, B, and C are all measured in meters, then the left-hand side would be, every term will be dimensionless, and likewise with the right-hand side, so it's satisfying the kind of dimension equations that we want. So we have another example to motivate this in this section, so let's look through it. In this case, this may be an inequality you're comfortable in solving, but let's just explore what we can do. Our motivation will be working towards this one. The motivation, one thing that we can look at is that when we have an inequality like this that's not, I guess, dimensionally consistent, there are different dimensions in the different terms. If we have this condition, which is often what happens, what motivates the need for vectorization that we are going to talk about later, or to work with conditions, which is what this last section of the slides we'll be looking at. What we can just try to do is to bump up every term to have the degree that we want. And so if A plus B plus C is equal to 1, we can just do that by multiplying where relevant A plus B plus C, which should be at the, that's what we do here. So our inequality that we saw 2 slides ago, this, we keep this the same because it says degree 2, but this, these 3 terms, we can multiply that by 1, so A plus B plus C to get degree 2. And then we can multiply the 4 over 3 by A plus B plus C squared to again get degree 2. Yeah. So that's what we've done. And then at least the dimensions are consistent. That does lead you towards, I guess, a more direct solution in this case. We'll come back to other reasons for doing this that come a little bit from this slide. The reason why we want to have that property of the dimensional consistency is that when you scale your, and again, this is how it comes back to the idea of units, when you scale every single variable by the same amount, then what happens is that your inequality will stay the same if you have dimensionally consistent units. That is the motivation we're trying to work towards. So in this case, when we didn't have dimensionally consistent units, the squared terms would scale by 4, the linear terms would scale by 2, the constant factor would not scale when you replace everything by 2 of itself. And so we want to move towards the case where we can express the equation in a certain way where we can have that scale, which is what we will be doing with normalization. So there's this long slide that I don't expect you to read the whole thing, but just get a little gist of what this is about as I've been trying to motivate up to here. The idea is similar to when you're proving cases, if you've done similar proofs before, where you say, oh, without loss of generality, I'm going to assume this is true. It's not exactly a without loss of generality claim that we're going to assume. In a certain sense, they're similar. But what happens is that if we have our equations are consistent on each side, our inequalities consistent on each side, then we might want to think about a convenient restriction to say that we're assuming that the kind of normalization of our vector will be in a certain way. So that might appear as assuming that a plus b is equal to 1 if we have the constraints that, constraints the inequality that is homogeneous. And that's similar to what, the reason why that is true that we can assume that is because otherwise you can just normalize to get to that position that you want in your equation and it will stay the same. Okay, so let's try this example to work through this. This equation is an example of equation that is homogeneous, as we've been trying to work towards. If A, B, and C are all have units of time, then the left-hand side, each term would have units of time. So it'll be time squared divided by time. And likewise on the right-hand side, it's all sum of time terms. And what we can do from here is, since we have a symmetry in the way that each of these denominators are the sum of the two terms that are not the one on the numerator, so if we have B and C on the denominator here, or we have A on the numerator, likewise with the other two, and then we have this conditional A plus B plus C, one convenient restriction would be something involving additions of A, B, and C. And we would want to do it in a way, the motivation coming from Jensen's inequality that we saw before, we would want to do it in a certain way that the functions that appear in each term have the same variable. So what does that look like? Let's see that explicitly if you didn't quite get what I was trying to go at. What we're going to assume is that A plus B plus C is equal to 1. We're allowed to do this. This is a homogeneous equation. We're allowed to make this assumption to say, if it's not, then without loss of generality, we can scale it down such that it is, and so forth. We're making that type of assumption so that what happens is we have, first thing you might observe, at least I observe, this equation looks prettier than this one. So if the equation looks better, it's going to be hopefully easier to solve. The looks aren't everything. And sometimes the hardest problems are the simplest ones. Just to justify, if you weren't following, the reason why the denominators change is because we're assuming that A plus B plus C equals to 1. We change that there as well. The B plus C, for instance, becomes 1 minus A. But then we get this equation that reduced our problem to. So proving this inequality reduces to proving this inequality down the bottom, and we can use Jensen's inequality. You might have to play around with it a little bit when you're trying to solve this yourself, but this is something you hopefully would think to try when you see equations that have the same variables in each term. We can prove, if you want to, that it's left as an exercise for the reader, so I will not be doing this since I'm not reading, you are. X squared over 1 minus x is continuous on negative infinity to 1. So that's nice for us. To let us say, so if that's nice for us, it lets us then say that we can apply Jensen's inequality to this function. That's something we've done a few times today, just to recap. we are also going to be using the fact that a plus b plus c is equal to 1. That's the reason why we go from here to here. But otherwise, we are just doing the regular thing we do with Jensen's inequality. The reason why the 1/3 shows up is because we need to make sure that we have the here was talking about the TIs, they have the sum to 1, so we say the TIs are all uniform, they're all 1/3. And so when you expand it out like this, 3 cancels when you bring the 1/3 after, if that makes sense. But if you plug in 1/3 to your function, then what happens is that you get 1 when you multiply it by the rate. Any questions on this? Just one thing to think about, A, B, and C are all positive, and we've made this without lots of generality assumption that A plus B plus C is the 1. One thing I was thinking about is that why are we allowed to restrict that we only have concavity when we're on the interval negative infinity to 1? Why is it that we're allowed to assume that that is the case? So if A, B, and C are all positive and they all sum to 1, then they can be at most 1. So they're strictly between 0 and 1, all of them, which means we don't have to worry about the fact that this concavity doesn't apply when we go above 1. So we are actually looking good. Okay, any concerns, questions, queries? I always say questions, queries, concerns. The additional one you're meant to say is arguments. Any arguments? No? Okay. Oh, yeah, note to me is that you can also use the angle form of Cauchy-Schwarz that we looked at with Jeff's topics to prove this from here, from this set, or even, I believe you can just do it, actually, yeah, you can just one-shot it from, so you can one-shot it from here with the angle form of Cauchy-Schwarz. Leave that as an exercise for the reader. Unfortunately, simple examples can usually be one-shotted by Jensen, so this does motivate the use of the normalization technique, but yeah, Jensen is a lot more powerful, though with some of the worksheet questions, you might need to think a bit more carefully. Okay, so let's move on. Some useful substitutions. So this would be our last section. These are just some more case-by-case situations that you can use and motivation as to why you would use them. For instance, if you see square roots in your inequalities and you have positive values, then what you would want to do is say, I hate square roots, let's replace them with squares. Which is the most natural thing to do. You would have done that if you did extension 2, say when you try to prove A and GM or something similar, it does show up. So let's look at an example. If we rewrite this inequality with our squares, you might recognize this as this inequality, which is one of the first couple ones you prove in extension 2 maths. It's a classic one. I'm sure you're all comfortable in proving this one. If you made it this far in the slides, congratulations on that, by the way. Just a recap is that to prove this one, what we do have to prove there, you can think about it as, just ignore the half here for a minute. If you add x minus y squared plus y minus x squared plus z minus x squared, you don't then set x minus y squared twice. 1 was meant to be y minus z squared. But you basically sum in all the different combinations of 2 of your 3 elements. That's what the CYC means. So the CYC is cyclic sum. You're summing over the cyclic possibilities. So x then y, y then z, z then x. So it's looping around. So x, y, z loops back around. You're taking consecutive ones. That's what it's meant to mean. The cyclic permutations. And you sum those up and get the squares. And you also get the times 2 at a time. Okay. So this is another lovely homogeneous equation. Ratio sub speaks for itself in the fact that if you have ratios in your equations, you may not want those. So let's get rid of them. The convenient fact is that when you have ratios, when you multiply x, y, and z, x, y, z together, you get 1, which is nice. You may want that as a condition, constraint in the equation. So this section is we're looking at some inequalities where we either add constraints or we look at constraints. So this is interesting to link to that. Let's look at an example. Obviously, this example has fractions in it. So we're going to get rid of those fractions. Two of the fractions, so one side of the fractions is easier to deal with than the other. If having x as a or b, we just replace x, y, z here, as we've done down here. But you would eventually get to this point if you do it yourself, but substituting in x, y, and z on the left, so the right hand side, it may take a while for you to work through it, but if you make this observation that x, y, z is equal to 1, that becomes a lot easier. You notice that a over c is 1 over z, which becomes x, y, and so forth. We can move forward from there. The inequality that is reduced down to grouping is this one, which is just a rearrangement of the inequality that we saw on this slide. So hopefully those two techniques are straightforward. I won't try to hope that this technique is straightforward, at least in the explanation of why we do it. Ravi sub. So the specific specification of this is that if you have triangle sides, so A, B, and C are the sides of triangles, there is this nice relationship with the in-center of the triangle that lets you do the substitution where you substitute into the variables y, x, and z, where the sum is kind of cyclic way again. That's useful, of course, when you have equations that have sums like these within them. Here's another form. This looks ugly, right? Again, we're going to say this equation looks ugly. What happens when we rewrite it in a different form? That's a lot of what inequalities in math is. You're trying to recognize established notions by rewriting things. It's crazy interesting. So we do our Ravi sub. What we can observe is that when we sub with what we chose A, B, and C to be, we get 2z, 2x, 2y in our different factors on our left-hand side. So what we then are trying to prove is that a, x, y, z on our left-hand side is less than or equal to our x plus y times y plus z times z plus x. This one is an application of the true case of A and GM. You can just really apply A and GM pairwise. So for each of these, the x plus y, you can compare that to 2 square root x y. That's A and GM if you take the square root of both sides. And then what happens is that you do that for each pair, y shows up twice as a square root, so you have one y here. Likewise, x shows up twice and square root shows up once there outside the square root. Square of square root x. Any questions? Okay. So just to link a bit more clearly, the reason why we do this, or why this works, is there is this link when, as I said before, this happens when A, B, and C are the side length of a triangle. What it turns out is that x, y, and z, they are real values that exist. They turn out to be the lengths related by the intersection of the in-center, the largest circle that you could draw that fits within your triangle. And so it's tangential on each side. That's why this x and this x are the same, because triangles going towards each other. You can kind of justify to yourself why this works, and then the result that you have is that the triangle inequality, I guess, algebraically says that both x, y, and z are all positive, so they're real values that exist very nicely. Okay, so you can review that later. Last one. So we made it this far. This one is a little bit trickier than the previous ones. But the reason why we do trig sub should be not too hard to understand. When you have an integral and it looks like you have say the square root of x squared minus 1, 1 minus x squared, that resembles one of the trigonometric identities, then you substitute with a trigonometric function. We can do the same here. So we do this when we have a condition that forces this pairwise product to equal to 1. What we do is let x, y, and z be tangents of half angles, so big A, big B, C, respectively. We do that such that those angles are all acute angles. So A, B, and C would all be acute angles. And positive acute angles. And let's look at the example we're going to use for this. We have a bit on the next slide, so that's what this arranged. Let's look at the example where we want to prove this. So prove something that involves this type of 1 plus x squared with square roots and such going on that motivates us to want to use trigonometric functions. So if we want to replace tan in some way, tan makes sense to use because with tan satisfies the identity 1 plus tan squared is equal to x squared. So for instance, if we're looking at this x over square root 1 plus x squared, if x is equal to, I'll say tan theta, or theta equals a over 2, and then for y will be b over 2. But if this happens, then this will become tan theta over square root 1 plus tan squared. As I said, this denominator becomes the square root of sec squared. So this becomes cosine times tan theta, which is sine theta. So just believing that this works and this works, then what you get is you can replace this inequality that looks a little bit ugly with a sum of sine functions. And so what we're going to use from here is, again, the finishing step is Jensen's inequality, very useful. But one thing we just want to explain is a condition that comes from this substitution, this is why it's particularly useful, is that if we substitute with these angles in this way, what happens is because this sum is equal to 1, then what would occur is that A plus B plus C, in terms of the angles, would then become pi. It's either pi or pi over 2. Let me clarify. Yeah, so the sum of half of this pi over 2, so the sum of the A plus B equals plus C equals to 1. Basically, kind of the stupid intuition behind that is that, for example, if you just had tan, if you just had tan A over 2 plus tan B over 2, just move some space. Or rather, I should say tan. If we just were dealing with tan alpha over 2, tan beta over 2, and we were told that, say, tan, so this is the case with two variables, I suppose, tan A over 2 and tan times tan B over 2 was equal to 1. Then basically the idea that we're using is that tan A plus B over 2, this comes from an identity you may remember from high school, that's equal to tan, that's basically what we tried part of there, that's tan A 2 plus tan B over 2 over 1 minus tan A over 2, tan B over 2. And I know this is quite informal, but what's basically happening is that since this equality holds, we're dividing by 0 here. And so tan a plus b over 2 would be infinity. And so that means since we're dealing with acute angles for a plus a and b, that means that a plus b has to be equal to pi, and likewise, applying a bit more general formula for the sum of three angles, you get a plus b plus c is equal to pi. And so that's useful because a plus b plus c shows up when you use Jensen's inequality. So let's apply Jensen's inequality on the next slide. We do that. One thing we need to be careful of is the domain that we're working over. The domain for us is not a problem because a over 2 will always be, a will always be between 0 and pi, or rather our x, because we only have to worry about acute angles. And so when we sum them up, we get to use the fact that sine pi over 6 is equal to half, that I still have memorized for some reason from high school. And that means that we have this 3 over 2 occurring on our right-hand side. One thing I forgot to check is that we didn't write on the left-hand side here, but it is important that x, y, and z are all positive here because that lets you extract an acute angle of a over 2 when you're trying to write this equation. That's the small detail. But yes, it's important that x, y, and z are all positive. Any questions? Okay, wonderful. Before I let you have pizza, you can look at this beautiful artwork from Kevin. I do want to say again, thank you for the presenters today, mainly Jeff and Via, and also the other people in our team that worked on this, these workshop slides. Most of these last sections were written by other people, and I'm just presenting them, so thank you to them. In terms of CPM events coming up, we have our DP workshop next Tuesday, 5 to 7, and we also have math circles occurring weekly from 2 to 5 p.m. on Fridays. Just come to join us. We'll have some problems like this problem sheet that we have here for today. We are trying to get back our problem of the week. That will be starting up roughly this week of term, weekly. We'll try to bring out some sheets for the problem of the week for those math circles. Otherwise, we'll have events throughout the term, so please join us again. If you want to try some of the questions from today, you can take one of these sheets. Otherwise, please scan the attendance form and then we'll let you have pizza. All the way back. I will actually end the stream though. So thank you everyone for joining us. Actually, we'll get the photo with the banner first.
Yes.
Yes, we need money, so please come to the front to...
Everyone, you have to close.
If you enjoy it, spread it.
Come people.
You can't improve the brightness, you don't close. Like that.